All right, class, welcome to Module 5, Water Resources and Climate Considerations. Today, we're going to explore how water plays a role in urban farming, especially in the face of climate change. We'll look at the rules, the markets, and the strategies that help farms not just survive, but thrive in cities. Think of this module as a bridge between the lab and the farm. Everything we study in science can be applied to real-world farming challenges. Innovation and sustainability go hand in hand here. As we move through this module, I want you to keep this question in mind. How do water laws and infrastructure, climate variability, and water-smart farming practices work together to shape California's water challenges and solutions? Keep this thought ready, because we'll come back to it at the end of the lesson. Now that we've introduced Module 5, let's dive into sustainable agri-food systems and the circular economy. We'll cover 3 lessons, each focused on understanding how water and climate shape urban farming in California. Lesson A. Every drop tells a story. First, we'll focus on California's major water sources. Remember the Colorado River, the State Water Project, and the Santa Ana River. These are the lifelines for our farms and cities. Next, we'll look at how interstate compacts, aqueducts, and dams distribute water across the state. For example, the Colorado River Aqueduct and the State Water Project move water hundreds of miles to reach urban areas. We'll apply this knowledge by looking at maps and tracing water from its source to the city. Then, we'll analyze infrastructure challenges. For instance, the Oroville Dam crisis showed how vulnerable our water systems can be. Finally, we'll evaluate the long-term sustainability of California's water supply. What happens if we don't adapt to growing demand and climate change? Lesson B. Climate knobs. Next, we'll discuss climate factors that affect water, our climate knobs. Remember the 3 main knobs: global warming, earlier snowmelt, and erratic precipitation. We'll understand how ENSO, meaning El Niño and La Niña, influences California's rainfall patterns. Then, we'll apply that knowledge to interpret data on evapotranspiration, rainfall variability, and snowmelt timing to predict water availability. We'll also analyze climate model projections for the inland deserts and discuss their implications for farming. At the end of this lesson, we'll evaluate which adaptation strategies, like conservation, reuse, or innovative technologies, are most effective for building resilience. Lesson C. Water-smart urban farming. Finally, we'll focus on water-smart practices for urban farms. Remember key tools and strategies: soil organic matter, drip irrigation, hydroponics, and vertical farming. We'll understand how building the soil sponge improves water productivity. Then, we'll apply this by scheduling irrigation using ET data and soil moisture sensors. Next, we'll analyze trade-offs between conventional farming, hydroponics, and vertical farming in water-scarce regions. Finally, we'll evaluate which water-smart practice is most viable for a case study farm and justify our reasoning. By the end of these lessons, you should be able to see how water management, climate knowledge, and smart farming practices come together to support sustainable urban agriculture. Let's think about a big question for Lesson A. What laws or agreements decide where our tap water comes from, and what problems can they cause? California's water doesn't just show up at our faucets on its own. It comes from places like the Colorado River, the State Water Project, and the Santa Ana River. But there are rules and agreements that decide who gets the water, how much they get, and when they get it. For example, the Colorado River Compact is an agreement that splits water between several states. That sounds fair, but it can cause problems, especially during droughts when there isn't enough water for everyone. Also, think about the Oroville Dam crisis. That showed us that even with rules in place, our water systems can have big challenges. So today, we'll explore how these laws and agreements affect where water comes from and how reliable it is. By the end of this lesson, you'll be able to explain how these rules shape our water supply and why that matters for both cities and farms. Did you know that Southern California imports more than half of the water it uses? That means most of the water we drink and use in our cities comes from far away. One big system is the State Water Project. It carries snowmelt from Northern California all the way south, about 705 miles, through the Central Valley to supply cities and farms. The California Aqueduct is the longest part of that route, stretching around 444 miles. Another major system is the Colorado River Aqueduct. It runs 242 miles west from the Colorado River into Southern California. On this map, you can see these major water routes highlighted in blue. These aqueducts are like giant water highways moving water from where it's available to where people need it. Take a moment to look at the map and notice how far this water travels. Think about what it takes to get water from hundreds of miles away to our taps every day. Take a look at this image. Most of California's water reserves are in the northern part of the state. But here's the challenge. Most people and farms live in the south. That means water has to travel a long way to get to where it's needed. To solve this, California built a massive system of canals, aqueducts, and reservoirs to move water from north to south. While this system works, it also creates ongoing challenges. Moving water over long distances takes a lot of energy, requires careful management, and can impact the environment. As we go through this module, we'll see how these challenges affect farms, cities, and the sustainability of California's water supply. Now let's talk about an important water agreement. The Water Treaty of 1922, also called the Colorado River Compact. This was the first interstate water treaty in the United States. It divided the Colorado River's water into two halves, giving 7.5 million acre-feet per year to each division of the basin. The upper division includes Colorado, New Mexico, Utah, and Wyoming. The lower division includes Arizona, California, and Nevada. This agreement made it possible for Southern California cities and desert farming to grow rapidly. Basically, it gave people and farms the water they needed to expand, even in very dry areas. Think about this. Without agreements like this, much of Southern California might not have been able to grow so much so quickly. Let's continue looking at the history of the Colorado River and the 1922 Water Treaty. In the early period, only Lake Mead existed and water levels went up and down moderately. Then came the 1950s drought. Low rainfall caused reservoir levels to drop noticeably. Between the 1960s and 1980s, Lake Powell was built, adding a lot of storage. Together, these reservoirs reached record high water volumes. But starting in the 2000s, a new drought began. This one was driven not just by low rainfall, but also by higher temperatures. Reservoir levels in Lake Mead and Lake Powell dropped sharply and stayed low for years. Today, reservoir volumes continue to trend downward. Warming, reduced snowpack, and higher evaporation are all contributing to less reliable water supplies. Even though the 1922 Water Treaty divided the Colorado River fairly, the Southwest now faces serious challenges. Cities and farms that rely on these reservoirs must adapt to changing conditions caused by climate change and ongoing drought. Now let's look at the State Water Project and the Oroville Dam, built in the 1960s. The SWP was constructed between 1961 and 1968. Its purpose is to move snowmelt from the northern Sierra over 400 miles south using a system of canals, tunnels, and 30 pumping and generating plants. One of the key pumping plants, the Edmonston Pumping Plant, can use up to 2 gigawatts of energy at peak times just to lift water over the Tehachapi Mountains. That's a lot of electricity. At the heart of the SWP is the Oroville Reservoir, which holds 3.5 million acre-feet of water. This reservoir not only stores water, but also provides hydroelectric power for the system. So, the SWP shows us how California moves huge amounts of water over long distances. But it also comes with big energy costs and engineering challenges. Let's take a closer look at the Oroville Dam. It stands 770 feet, or 235 meters, tall, making it the tallest dam in the United States. The dam has three main purposes: providing water supply, generating hydroelectric power, and controlling floods. Its capacity is 3.4 million acre-feet of water, which is a huge amount, enough to supply millions of people and farms. Think about that for a moment. This single structure stores and moves massive amounts of water, helping cities and farms across California while also producing electricity. Now we're going to talk about a dramatic event: the 2017 Oroville Spillway Crisis. The question is, what happens when the tallest dam in the U.S. starts to break? Extreme rains overwhelmed the spillway, which forced mass evacuations. In total, 188,000 people had to leave their homes for safety. This crisis shows how climate extremes and aging infrastructure can combine to create serious problems. Over just 50 days, 4.4 million acre-feet of runoff flowed through the dam, with peak releases reaching about 100,000 cubic feet per second. The damage and repairs cost around $1.1 billion. This event reminds us that managing water isn't just about moving it from north to south. It also involves preparing for extreme weather and maintaining massive infrastructure. Let's recap the timeline of the Oroville Dam and the 2017 spillway crisis. The dam was constructed between 1961 and 1968. Its main purpose was to store snowmelt from the northern Sierras and send it south to cities and farms. Fast forward to 2017. Extreme rains tested the dam's spillway, leading to the crisis we just discussed. Today, the event serves as a reminder that climate extremes put pressure on our aging infrastructure. It shows how important it is to maintain these systems and plan for the unexpected. So, when we think about water management, we have to consider not only how we move and store water, but also how safe and resilient our infrastructure is under changing climate conditions. Now, let's look at who controls the water in Southern California. At the top, we have the California Department of Water Resources, or DWR. They run the State Water Project, which includes aqueducts, dams, and pumping plants. Basically, they manage the water coming from the north. Local agencies then buy water from DWR to supply their communities. Some of the main local agencies include the San Bernardino Valley Municipal Water District, the San Gorgonio Pass Water Agency, and the Metropolitan Water District of Southern California. So, water flows from the State Water Project to these local agencies, and then finally to homes, farms, and businesses. When you think about it, managing water is a huge system that involves both state level and local level coordination. Now, let's follow the path of water from Northern California to Southern California. The main canal is the California Aqueduct, shown as the blue line on the map. This canal carries water hundreds of miles south. The aqueduct has two main branches. The west branch supplies Pyramid Lake and Castaic Lake in the Los Angeles area. The east branch supplies Silverwood Lake, Crafton Hills Reservoir, and Lake Purries in Riverside County. So, this system moves water from its northern sources and delivers it to multiple regions in Southern California. It's like a giant network of water highways connecting north to south. Now let's see how water actually moves from Northern California to Southern California. Pumping plants, shown with orange arrows, push water up and over mountain ranges. A good example is the Pear Blossom pumping plant. Without these pumps, the water wouldn't be able to reach the southern parts of the state. Reservoirs, shown with blue icons, act as storage points. For example, Pyramid Lake helps regulate flows and provides a reliable water supply for cities and farms. So, it's not just canals moving water. Pumping plants lift it, and reservoirs store it along the way to make sure there's enough for everyone. Now let's look at how water moves from the Colorado River to Southern California. The Colorado River Aqueduct is built and operated by the Metropolitan Water District, or MWD. It stretches 242 miles and includes open canals, siphons, reservoirs, tunnels up to 16 feet wide, and 5 pumping plants. Even though it was built a long time ago, ongoing upgrades keep the system reliable so it can continue supplying water to millions of people and farms. Think of this aqueduct as another giant water highway, moving water across deserts and mountains to meet the region's needs. Now let's explore the infrastructure behind the State Water Project that brings water from the Northern Sierra to Southern California. This is a partnership between the Metropolitan Water District, or MWD, and the state of California. Together, they manage a huge system of assets, including 34 reservoirs, 20 pumping plants, 4 pump generators, and 5 hydroelectric plants. The pipelines and canals stretch about 700 miles, with the California Aqueduct itself covering 444 miles. The aqueduct is massive, up to 110 feet wide and 32 feet deep in some sections. So, this system shows just how much planning and engineering it takes to move water hundreds of miles to supply cities and farms. Now let's follow water all the way from the aqueducts to your tap at home. Imported water spreads across the Metropolitan Water District's service area, which covers 5,200 square miles. Before it reaches homes, water is either treated at one of 5 regional treatment plants or delivered raw to be purified later by local agencies. The distribution network includes 830 miles of large pipelines and about 400 agency turnouts that connect to local taps. So, after traveling hundreds of miles from Northern California or the Colorado River, water finally arrives at your home thanks to this huge and complex system. Now let's focus on our local water sources here in Riverside. Most of Riverside's drinking water comes from groundwater wells in 2 basins, Bunker Hill and Riverside. About 60% of the water comes from Bunker Hill. Since 2009, we haven't needed to import water because local supplies now cover demand, even during dry years. These basins are refilled or recharged by the Santa Ana River and storm runoff. This shows how local water systems can provide reliable supplies when they're managed carefully. Now let's zoom out and look at the Santa Ana River watershed, basically our shared water backyard. It covers a 2,650 square mile area and is home to over 6 million people. The watershed spans 4 counties: Orange, Riverside, Los Angeles, and San Bernardino. The river starts in the mountains and flows all the way to the Pacific Ocean. Here's a fun way to think about it. A watershed is like a giant bathtub. All the rain that falls in the area eventually flows to the same drain, which is the river. Understanding watersheds helps us see how water moves across our region and why everyone's actions from cities to farms affect our shared water supply. Let's take a look at where Southern California gets its water. About 45% comes from local sources, like groundwater and nearby rivers. The remaining 55% is imported through some amazing engineering projects. About 25% comes from the Colorado River, which travels hundreds of miles through aqueducts to reach us. Another 30% comes from Northern California snowmelt, delivered via the State Water Project. So almost half our water is local, and the other half depends on huge systems that move water across long distances. This shows how much planning and infrastructure it takes to supply water to millions of people and farms. Now let's look at a case study. How Los Angeles got its water from Owens Valley. The old way, LA took water over 200 miles from Owens Valley. This caused big problems. Farmers lost crops, rivers and lakes dried up, and local residents fought back. This conflict became known as the California Water Wars. The new approach focuses on local solutions, capturing rainwater, recycling water, and conserving what we have. These practices help refill local groundwater and reduce dependence on water from faraway sources. This case study shows that water management isn't just about moving water long distances. It's also about using local resources wisely and sustainably. Continuing with our Owens Valley case study, let's look at the benefits of the new approach for Los Angeles. First, it provides reliable water for about 4 million people. That means the city can grow and thrive without constantly worrying about shortages. Second, it reduces dependence on faraway water sources, which makes the system more resilient. There are also environmental benefits. Some restoration has occurred at Owens Lake, helping the ecosystem recover. But there's a trade-off. Water decisions can create both growth and conflict. Even with better management, choices about water use can still affect people and the environment in different ways. This shows that managing water is always a balancing act between human needs and environmental health. Let's start with the big picture of California's water. Our water comes from natural sources, rain, snow, rivers, and groundwater, as well as human-built systems like dams, aqueducts, and pumps. Climate change is making this system less predictable. We're seeing hotter days, less snow, and rainfall that doesn't follow the old patterns. On top of that, infrastructure adds challenges. Water has to be stored, moved, and managed carefully, and if any part fails, it can create problems. Can anyone think of a time when water shortages or flooding affected your community? Now let's look at systems thinking in action. Water connects people, farms, cities, and nature, so it's all linked. Timing and flow are really important. Changing one thing can affect many other parts of the system. Thinking in systems helps us avoid quick fixes that might create new problems later. For example, Sierra snowmelt isn't just snow, it provides water for farms, cities, and ecosystems downstream. Can anyone think of another example where one change affects a whole system? Let's talk about nature's water loops. Nature recycles water in a cycle. Rain falls, flows into rivers, evaporates, and then falls again as rain. A good example is Sierra snowmelt. It melts into rivers, evaporates, and eventually becomes new snow. The big idea is that nature cycles water very efficiently, and humans can learn from these loops. But humans often break these natural cycles, which creates challenges, like water shortages, but also opportunities to improve the system. Can anyone think of a way humans might accidentally break these loops? Now let's focus on humans in the water system. People can break natural loops. For example, overpumping groundwater can lower water levels over time. Sometimes this creates feedback loops. Hotter nights lead to more irrigation, which then lowers groundwater even further. Water patterns are also uneven, with boom and bust years. Some years are very wet, others very dry. But small changes can make a big difference, like using drip irrigation, adding compost, or creating a soil sponge. Can anyone think of other small actions that could help manage water better? Next, let's compare two types of water systems. A linear water system moves water in one direction, from source to use to waste. This often wastes water and can put a strain on supplies. In contrast, a resilient or circular water system captures, reuses, and recycles water instead of letting it go to waste. Thinking in loops like this helps communities and farms manage water more reliably, especially during droughts or unpredictable rainfall. Can anyone think of an example of a circular water system they've seen, like graywater recycling or rainwater harvesting? Let's look at some real world examples of water management. First, atmospheric rivers bring 30 to 50% of California's rain, but they also cause most of our floods. The Santa Ana Basin relies on local groundwater, which helps reduce the need for imported water. And hydroponics or vertical farms can reuse up to 90% of their water, showing how technology can mimic natural loops. These examples highlight how understanding water loops and timing is key to managing water efficiently. Which of these examples do you think has the biggest potential to help California in the future? Now it's your turn to apply what we've learned. In your groups, map your community's water system using systems thinking. Show the inputs, where water comes from, the outputs, where it goes, and any feedback loops, how one part affects another. Then add one resilience strategy like drip irrigation, stormwater capture, or hydroponics. Finally, identify one weak point in your system where water could be lost or mismanaged. I'll walk around and ask questions to help you think through your maps. Remember, small changes can have a big impact. To wrap up, let's have a class discussion. First, think about where your water comes from and identify one weak point in that system. Next, consider which climate stress matters most for your community: hotter weather, less snow, or shifting rainfall. Then, if you could add just one resilience strategy to your city, what would it be? Finally, think about the ripple effects. Who benefits from your choice and who might be left out? Let's hear some ideas from each group. And remember to explain your reasoning. Now we have an optional activity called Water Detective. This is a think, pair, share, and team design activity where students will trace the journey of a drop of water to Southern California. Here's what you will do. Pick a water source, like the Colorado River, a local river, or a reservoir. Map its journey and key infrastructure, think aqueducts, canals, pumping plants, or reservoirs. Identify the biggest stress point along the way. This could be a place where water shortages, infrastructure challenges, or environmental concerns happen. Link this stress point to a global issue. For example, you could connect water scarcity in California to droughts in other parts of the world. Suggest one solution to address this stress point. Present your plan to the class in 1 to 2 minutes. This activity helps you apply what we've learned about water sources, infrastructure, and challenges while thinking creatively about solutions. Work together, be detailed in your maps, and be ready to explain your reasoning. Let's take a moment to review what we've learned so far. I'll read the questions, and you can think about the answers. 1. Where does most of Southern California's water come from? 2. What was the purpose of the 1922 Colorado River Compact? 3. What happened during the 2017 Oroville spillway crisis, and what does it show us about water infrastructure? Take a minute to discuss these questions with a partner or jot down your answers. Then we'll go over them together as a class. Remember, these questions help us connect water sources, laws, infrastructure, and climate challenges in California. Here are the answers to the review questions. 1. More than half is imported, mainly from the Colorado River Aqueduct, 242 miles, and the State Water Project, 705 miles. 2. It divided the Colorado River's water between the upper CONMUTWY and lower CAAZNV basins, enabling the growth of Southern California cities and farms. 3. Heavy rains overwhelmed the Oroville Dam spillway, forcing 188,000 people to evacuate and costing over $1.1 billion in repairs. It shows how climate extremes plus aging infrastructure threaten water security. These answers reinforce the key points about where water comes from, how laws manage it, and why infrastructure and climate matter. Now we move to Lesson B, Climate Knobs. The question for this lesson is, what climate forces affect water availability the most? Climate has a big impact on water supplies. In California, 3 main climate knobs influence how much water is available: global warming, earlier snowmelt, and erratic precipitation. We'll also look at how El Niño and La Niña, known as ENSO events, change rainfall patterns in the state. These factors affect rivers, reservoirs, and even groundwater, which in turn influences farming, cities, and water management. By the end of this lesson, you should be able to explain which climate forces have the biggest impact on water availability and why understanding them matters for planning and sustainability. Let's look at the 3 main climate forces that shape California's water supply. First, global warming. Rising temperatures mean less snowpack in the mountains, which reduces the amount of water we can store for later use. Second, earlier snowmelt. when snow melts too early in the year. There's less water available during the hot summer months when we need it most. Third, erratic precipitation. Some years bring heavy floods, and other years bring long droughts. This makes water supplies unpredictable and harder to manage. Together, these three climate forces act like knobs that turn the amount and timing of water available for cities, farms, and ecosystems. Now let's see how greenhouse gases affect our water. Warming, earlier snowmelt, and unpredictable rain all change the water supply. Greenhouse gases like carbon dioxide, CO2, and methane, CH4, trap heat in the atmosphere. This leads to less snow, earlier snowmelt, and more water needed for farms during hot months. At UCR, the mobile lab measures these gases to study how human activities are affecting both climate and water. By tracking greenhouse gases, scientists can better predict changes in water availability and plan for sustainable water management. Now let's focus on California's inland deserts. These areas are already hot and dry. By the year 2100, temperatures could rise 8 to 14 degrees Fahrenheit. That means even less water and higher demand from people, farms, and cities. Rainfall is unpredictable, which makes it harder to store water for farms, cities, and tribal lands. Water is essential here not just for agriculture, but also for tourism and renewable energy. This image shows a regional report on the inland deserts. Scientists use reports like this to study how rising heat, shifting rainfall, and limited water affect people, nature, and the economy. It helps planners and communities prepare for the future. Now let's look at mountain snow in California. Snow in the mountains melts into the Sacramento and San Joaquin rivers, which supply water to farms, cities, and ecosystems. Over the past 100 years, spring runoff has decreased, about 8% less for the Sacramento River and 7% less for the San Joaquin River. Snow is melting earlier in the year, which means less water is stored for summer when it's needed the most. Year-to-year changes still happen, but the long-term trend shows that water is becoming less reliable. This is a big challenge for agriculture and cities that depend on a steady water supply. Let's examine snowmelt runoff and how it has changed over time. The graphs compare past river runoff from 1931 to 1960, with more recent data from 1991 to 2020. For the Sacramento River, peak snowmelt runoff now happens earlier in the year than it used to. This means less water is available in summer when farms and cities need it most. For the San Joaquin River, runoff timing has stayed about the same, so the changes aren't uniform across the state. The key takeaway is that climate change is shifting when water is available, especially for the Sacramento River, making summer water supplies less reliable. Now let's talk about how hotter nights affect water needs for crops. Evapotranspiration, or ET, measures how much water the air would pull from a perfectly watered crop. Scientists calculate it using climate data. Hot nights increase ET because the air can hold more moisture. In inland deserts, where it's already dry, hotter nights mean crops need even more water to stay healthy. Dr. Hopkins' climate change assessment for California predicts that water demand for farms will continue to rise in the future. This shows how climate change affects not just water supply, but also water demand for agriculture. Now let's look at how temperatures have changed across California. Panola shows California's average temperature since 1895. The red line is the 11-year average, and you can see a steady rise over time. Overall, California is getting warmer. Panel B shows a map of drought conditions. Most of the state is experiencing moderate to severe drought, highlighted in orange and red. Warming makes these dry conditions worse. Panel C compares temperature increases in different regions. All regions are warming, but some areas, like the South Coast and Mojave Desert, are heating faster than others. These images show how rising temperatures impact water availability and stress both natural ecosystems and human water use. Here we're looking at the balance between water supply and water demand. On the supply side, rainfall is shown in lavender or purple for more rain and brown for less rain. You can see that winters are tending to get wetter, but spring, summer, and fall are becoming drier. This means California's water supply is becoming less reliable over the year. On the demand side, we look at ET0, that's the reference evapotranspiration, or how much water the air would pull from a perfectly watered crop. The copper and brown colors show higher water demand. As the air warms, it gets thirstier and pulls more water from the soil and plants. Demand for water is increasing in every season, especially winter and spring. So overall, supply is going down while demand is going up. This creates a growing challenge for farmers and communities in California. ENSO stands for El Niño Southern Oscillation. It's a natural climate pattern that changes rainfall and temperature across the Pacific Ocean, and it strongly affects California's weather. During El Niño years, Southern California usually gets wetter winters. This extra rain can help refill reservoirs, but it also brings risks like flooding and storm damage. During La Niña years, Southern California usually gets drier winters. That raises the risk of drought and water shortages, while Northern California may get more rain. For SoCal farmers and cities, La Niña means planning ahead for less water. Why does this matter? Because if we know an El Niño or La Niña year is coming, California can prepare, whether that means getting ready for floods or tightening water use. Let's look at how rainfall is changing in California, especially in the inland deserts. These areas are already very dry and unpredictable. On average, they get about 5 inches of rain per year. But some years it can be as low as 1.5 inches or as high as 10.75 inches. Rainfall also varies by location and elevation, ranging from about 3 to 8 inches per year. Climate models suggest that average rainfall might not change much overall, less than 10%. But the big change is that year-to-year swings are getting bigger. The driest years could be up to 50% drier than before, and the wettest years could be 40 to 65% wetter. This means water management is becoming more challenging because we have to plan for both extremes, droughts and floods. Now let's talk about atmospheric rivers, or ARs. These are long, narrow streams of humid air that come from the Pacific Ocean. They bring a huge amount of water to California, about 30 to 50% of the state's rain and roughly 40% of the snow in the Sierra Nevada. But they also carry risks. ARs are responsible for about 80% of major floods in California. The key idea is that managing ARs is really important. If we can anticipate and prepare for them, we can capture water safely, protect communities from floods, and maintain a reliable water supply. Let's see how scientists track atmospheric rivers, or ARs. Think of ARs as rivers in the sky, long, narrow bands of heavy moisture in the air. Scientists use planes, satellites, and sensors to monitor ARs before they hit California. This helps predict where rain and snow will fall, which is important for both safety and capturing water. One method is called Forecast-Informed Reservoir Operations, or FIRO. Using AR forecasts, reservoir managers can decide when to hold or release water instead of dumping it too early. The goal is to save more water for dry months while keeping communities safe from floods. Now let's look at a case study from Australia's Millennium Drought, which lasted from 1997 to 2009. The old way. Farmers in Southeast Australia relied heavily on seasonal rains and rivers. When a decade-long drought hit, crops failed, reservoirs dried up, and losses reached billions of dollars. The new approach focused on adaptation. Farmers shifted to drought-tolerant crops, like sorghum. Cities invested in desalination plants and water recycling programs. They also improved climate forecasting and implemented stronger drought policies. This case study shows how regions can respond to prolonged drought by using both technology and smart planning to protect water supplies and livelihoods. Continuing with the Australia case study, let's look at the benefits of their new approach to managing drought. First, it reduced vulnerability to rainfall variability. Farmers and cities were less affected by dry years. Second, it diversified the water portfolio. Instead of relying only on rivers, they used other sources like desalination and recycled water. Third, farming practices adapted to a hotter, drier climate, making agriculture more resilient. This case study shows how turning climate knobs, like drought, heat, and rainfall changes, forces both cities and farms to adapt and plan for a changing climate. Now we have an optional activity called Climate Detective. This is a think, pair, share, and team design activity where students will explore how a single climate knob affects California's water supply. Here's what you will do. 1. Pick one climate knob, such as global warming, earlier snowmelt, or erratic precipitation. 2. Trace how this knob affects water supply across California. 3. Identify the biggest stress point where water shortages or risks are most severe. 4. Brainstorm one solution to address the problem. 5. Share your story in a quick pitch or during a gallery walk with the class. This activity helps you apply what we've learned about climate forces, water supply, and problem solving in real-world scenarios. Work together, think critically, and be ready to explain your reasoning. Let's review what we've learned in Lesson B about climate and water. Here are 3 questions to think about. 1. What are the 3 climate knobs that control California's water supply? 2. How does El Nino differ from La Nina and its effects on California's rainfall? 3. Why does earlier snowmelt create problems for water supply? Take a minute to discuss these with a partner or jot down your answers. Then we'll go over them together as a class. These questions help us connect climate patterns, water availability, and the challenges that farmers and cities face. Here are the answers to our review questions from Lesson B. 1. The three climate knobs that control California's water supply are global warming, earlier snowmelt, and erratic precipitation. 2. El Nino usually brings wetter winters to Southern California, which can help refill reservoirs, but may also cause flooding. La Nina brings drier conditions, increasing the risk of drought. 3. Earlier snowmelt means water runs off sooner in spring. This can increase flood risk and leaves less water stored for summer, making drought conditions worse. These answers reinforce how climate patterns directly affect water supply, risk, and management in California. Now we move to Lesson C, Water Smart Urban Farming. Here's a question to think about. If you wanted to save water while farming, what's the first thing you would try? Water smart farming involves strategies that use less water while keeping crops healthy. This could include improving soil health, using drip irrigation, or trying hydroponics or vertical farming. As we go through this lesson, you'll learn how farmers and urban growers can make smart decisions about water use, measure soil and crop needs, and choose the best techniques for saving water in real-world settings. Step 1 in growing more with less water is to build the soil sponge. Adding organic matter to soil helps it hold more water. Better soil means more water is available for plants and less water runs off the surface. Farmers track several metrics to see how healthy their soil is. Percent of soil organic matter, or SOM. How fast water soaks in, called infiltration. Soil density, also known as bulk density. By improving the soil sponge, farmers can make crops more resilient to dry conditions and save water while growing more food. Step 2 is to match water to crop demand. This means only watering crops when they actually need it. Farmers use weather or soil data to guide irrigation. For example, ET0 tells us how much water the air is pulling from crops, and crop water needs tell us how much each plant type requires. Some key metrics farmers track are ET0, or atmospheric demand for water, crop coefficient, called KC, which adjusts water needs for different crops, soil moisture or water tension, which tells us how much water is available in the soil. By matching irrigation to crop demand, farmers avoid wasting water while keeping plants healthy. Step 3 is to close the loop. This means recycling water and nutrients to make farming more efficient. Farmers can add compost or biochar to improve soil and help it hold water. They can also try hydroponics or other closed systems that reuse water and nutrients. Some key metrics to track include application rates to see how much water and nutrients are used, energy costs, since pumping and moving water takes power, food safety to ensure recycled water or nutrients don't harm crops. The goal is simple: get more crop per drop of water. Closing the loop helps farmers save water, reduce waste, and grow more sustainably. Now let's learn about soil organic matter, or SOM. Soil organic matter is made of once living things: plants, animals, and microbes. It is dark, spongy, and earthy smelling. Usually, SOM accounts for less than 5% of the total soil volume, but even a small amount is very important. Where does it come from? Plants use sunlight, CO2, and water to make organic compounds. These compounds then cycle through plants, animals, and microbes, eventually becoming soil organic matter. Microbes are a critical part of this process. They produce glues called polysaccharides that bind soil particles, creating a stable, spongy structure. SOM acts like nature's sponge, helping soil hold water and nutrients, which is critical for growing healthy crops while saving water. Let's look at what soil organic matter, or SOM, actually does. It provides a source of carbon and nitrogen for plants. It holds soil together, which prevents erosion. It helps plants grow by storing nutrients that they can use over time. It prevents soil compaction, keeping soil loose and healthy. How does it work? Plant leaves and roots break down over time. Decomposers like worms, fungi, and bacteria recycle this material. The soil then stores nutrients and water, which allows plants to grow stronger and more resilient. Think of SOM as the soil's natural sponge and pantry, holding both water and nutrients for crops. Now we're going to learn about soil texture and how it affects water holding capacity. Here are some key terms. A. Saturation. All the soil pores are full of water, and any extra water drains freely under gravity. B. Field capacity, FC. The amount of water left in the soil after excess has drained, usually about 24 hours for sandy soils and 2 to 3 days for silt or clay. C. Permanent wilting point, PWP. The soil is so dry that plants can't take up water and they can't recover, leading to permanent wilting. D. Available water capacity, AWC. This is the water plants can actually use, which is the water between field capacity and permanent wilting point. You can estimate it using the rooting depth and water available per unit depth. Understanding these terms helps farmers know how much water soil can store and how often crops need irrigation. Here's a graph showing how much water different soils can hold. Sand drains very fast, so it holds less water for plants. Clay holds more water, so more is available for plants, but it drains slowly. Loam is in between sand and clay, which often makes it the best soil for farming because it balances water retention and drainage. The wilting point is where soil is too dry for plants to take up water, so crops start to suffer. By understanding soil texture, farmers can plan irrigation more efficiently and know how long soil will supply water to crops. Now let's talk about compost and how it helps soil hold water and improve infiltration. The compost cycle works like this. 1. Food scraps and organic waste are collected and turned into compost. 2. Compost is transported and applied to farm fields. 3. Healthy soils support crop growth and better harvests. 4. The crops are sold, eaten, and eventually, food waste re-enters the cycle. Adding compost improves soil structure, increases water retention, and helps crops grow stronger with less irrigation. It's a great example of turning waste into a valuable resource for farming. Now let's look at how compost can benefit soil and crops. First, compost helps soil hold more water, which means plants can survive better during dry periods. It also adds nutrients like nitrogen, phosphorus, and potassium. These are essential for plant growth and health. Compost supports soil life, including worms, microbes, and fungi, which all play important roles in keeping soil healthy. It also makes soil easier to work, so planting and harvesting are simpler and less labor-intensive. Compost stores carbon, which helps fight climate change by keeping carbon out of the atmosphere. It reduces erosion, protecting soil from washing or blowing away during storms. Compost can also boost crop yield and quality, giving farmers healthier, more productive plants. And finally, it can help fight weeds, pests, and diseases naturally, reducing the need for chemical interventions. Next, let's talk about biochar. So, what is biochar? Biochar is a carbon-rich, charcoal-like soil amendment. It's made from plant wastes such as wood, shells, or leftover crop materials. Biochar is charcoal-like and very porous, which means it can hold water and nutrients in the soil, helping plants grow better. It also improves overall soil health and supports stronger, healthier plant growth. By holding water and nutrients efficiently, biochar can reduce the need for frequent irrigation and extra fertilizers, which is better for the environment and saves resources. Biochar also stores carbon, helping to fight climate change by keeping carbon out of the atmosphere. Finally, biochar is resistant to decay, so it lasts a long time in the soil, making it a durable solution for improving soil quality. Now let's look at how biochar works in the soil. In coarse textured soils, like sandy soils, water drains very quickly because the sand particles don't hold it well. You can think of sand as having big gaps where water just slips through. When we 1009 in biochar particles, which you can see here as the black pieces, they create pores and surfaces that trap and hold water. As a result, instead of water draining away, more water stays in the soil, where plant roots can access it. This means plants have better access to water during dry periods, helping them grow stronger and healthier. Next, let's explore how cover crops and mulch help keep water available for plant roots. First, cover crops are living plants that grow between main cash crops. They protect and build soil, improve structure, and help water infiltrate by creating root channels and improving soil aggregation. They also reduce runoff and erosion. Cover crops do use water while they are growing, so it's important to manage the species and timing of termination carefully. Cover crops also build soil organic matter. Legumes can fix nitrogen, while non-legumes can scavenge excess nitrogen. They can suppress weeds, and your choice of species can also influence pests and beneficial insects. In California, cover crops are usually seeded in the fall or winter, rely on winter rains, and should be terminated before the peak water demand of the main crop. Let's focus on the main benefits of cover crops and organic mulch. Both cover crops and mulch help protect the soil from sun and wind, which prevents it from drying out too quickly. They also increase water infiltration, meaning more water can soak into the soil and reach plant roots instead of running off the surface. Finally, they reduce evaporation, keeping more moisture in the soil for plants to use. So, whether it's living plants between crops or a layer of organic material on top, both strategies help keep water where roots can access it efficiently. Now let's talk about drip irrigation, a highly efficient way to water crops. Drip irrigation delivers water directly to plant roots, which makes it very efficient. Over 90% of the water goes to the plants, meaning there is much less waste compared to traditional irrigation methods. Because the water goes straight to the soil, it keeps leaves dry, which helps reduce plant diseases that thrive on wet foliage. Drip irrigation also prevents nutrient loss and soil erosion because water isn't running off the surface and washing away valuable soil or fertilizer. It's a highly precise and scalable system, so it can work on small gardens or large commercial farms. Drip irrigation can also be combined with ET-based scheduling, which means watering happens at the right time based on evapotranspiration, ensuring plants get exactly what they need without wasting water. Next, let's explore subsurface drip irrigation, or SDI. This is a type of drip irrigation where the drip lines are buried below the soil surface. There are two main ways to install SDI. Deep burial. The drip line is buried 10 centimeters or more below the surface. This placement protects the lines, so they can last years or even decades. Deep burial is ideal for long-term irrigation systems. Shallow burial. The drip line is placed just below the soil surface. This helps reduce surface disruptions from things like wind or foot traffic, and it keeps water close to plant roots where it's needed most. Both methods aim to deliver water efficiently while protecting the irrigation system, but the choice depends on the crop type, soil, and long-term goals of the farm or garden. Now let's talk about irrigation maintenance, which is key to keeping systems running efficiently. First, it's important to schedule watering using evapotranspiration, data, or sensors, so plants get water when they need it most. Next, always keep the drip lines clean by using filters and treating the water if necessary. This prevents blockages and ensures water flows properly. To further prevent clogs, some systems use a small chlorination dose to control algae or bacterial growth inside the lines. Finally, it's important to check for leaks and pests regularly, because even small problems can waste water and reduce system effectiveness. Proper maintenance ensures the irrigation system is efficient, long-lasting, and reliable for your plants. Next, let's focus on irrigating only what and when the crop needs. Soil moisture sensors are tools that tell you when the soil is getting dry, so you can apply water only as needed. It's important to place sensors at multiple soil depths, because moisture levels can vary between shallow and deep layers. You should start watering when the shallow sensors show dry readings, and stop watering when the deep sensors show high wet readings. This ensures that plants get enough water without wasting it. Finally, check sensors regularly and adjust your drip or subsurface drip irrigation schedules as needed, because conditions like rainfall, temperature, and plant growth can change water requirements. Using soil moisture sensors helps save water, improve crop health, and reduce over-irrigation. Now let's look at 3 common types of soil moisture sensors used for irrigation. A. Tensiometers measure how hard plant roots are pulling water from the soil. This is often called negative pressure, measured in kilopascals, kPa. It helps us understand how much effort plants need to access water. B. Granular matrix-based sensors measure water tension between soil particles. This gives us an idea of how tightly water is held in the soil and whether plants can easily access it. C. Capacitance-based sensors show the percentage of water in the soil and can provide soil moisture graphs over time, which is very helpful for monitoring trends and adjusting irrigation schedules. Each sensor type gives slightly different information, but all are useful for deciding when and how much to irrigate. Next, let's talk about closed-loop growing systems, specifically hydroponics. Hydroponics is a method where plants grow without soil, using nutrient-rich water instead. These systems are usually in a controlled environment, like a greenhouse or growth chamber, which allows precise control over conditions like light, temperature, and humidity. There are several advantages to hydroponics. It can use up to 90% less water compared to traditional soil-based farming. Because nutrients and climate are controlled, plants often grow faster. No soil means there are fewer pests and diseases to worry about. However, there are also some challenges. Hydroponic systems are expensive to start. They require specific skills and maintenance. Routine care for pumps and filters is necessary to keep the system running smoothly. Overall, hydroponics is a water efficient and fast growing system, but it requires careful management and investment. Now let's talk about vertical farming, another type of closed loop growing system. In vertical farming, plants grow in stacked layers, often in a controlled environment like a greenhouse or indoor facility. This allows for year round farming regardless of outside weather conditions. Some advantages of vertical farming include it saves space, allowing more plants to be grown in a smaller area. Farmers can achieve year round harvests, which improves food availability. Because vertical farms can be built near consumers, there is less transport and fewer emissions, making it more environmentally friendly. However, there are challenges as well. Vertical farming is expensive to start. It uses high energy, especially for LED lights and climate control systems. Not all crops are suitable for vertical farming, so choices may be limited. Overall, vertical farming is a space-efficient and sustainable method, but it requires careful planning and significant energy investment. Let's look at a real-world example of hydroponics. Lettuce cultivation in Arizona. This slide shows data on annual lettuce yield, annual water use, and annual energy use, including a breakdown of where energy is consumed in the system. Hydroponics can be energy intensive, especially for lighting, pumps, and climate control. However, it is an ideal strategy for regions that are water scarce but have access to plentiful renewable energy sources like solar, wind, or geothermal power. By combining hydroponics with renewable energy, farmers can grow crops efficiently without overusing limited water resources, making it a sustainable solution for dry regions like Arizona. Now let's look at a case study from Singapore and how closed-loop farming changed their food system. The old way. Singapore used to import over 90% of its food because the country has very limited land. This made them vulnerable to global supply chain disruptions, like shipping delays or price spikes. The new approach. Sky Greens built vertical hydroponic towers that recycle water, allowing them to grow leafy greens locally. These farms are powered by solar energy and use 90% less water than conventional agriculture. This is a great example of how closed-loop farming can reduce reliance on imports, save water, and produce food locally, even in a place with very limited land. Continuing with the Sky Greens example, let's focus on the benefits of the new closed-loop approach. First, it boosts food security in Singapore, a country with very limited land. By growing food locally, they are less dependent on imports. Second, it saves water and reduces transport emissions, making the system more sustainable and environmentally friendly. Third, it creates jobs in high-tech urban agriculture, giving people opportunities in innovative farming technologies. Overall, this is a clear example of how technology and closed-loop systems can sustainably feed dense urban populations, even in places with little available land. Now we have an optional activity called Smart Water Advocate. This is a think, pair, share, and team design activity where students will debate which water smart strategy, or lever, is the best for saving water. Here's how it works. Each team will get one lever, either soil sponge match to crop or close the loop. Your task is to make a 2-minute case for your lever. Include 1. The main benefit of your strategy. 2. A challenge or limitation and one possible solution or fix. 3. An example of how it can be applied in real life. After the presentations, the class will vote on which strategy they think is best. This activity encourages you to think critically, collaborate with your team, and communicate your ideas clearly. Now let's do a quick review of what we've learned. I'll read the questions, and we can discuss them together. 1. What are the 3 components of water smart farming? Think about the levers we've discussed. Building soil health, matching crops to conditions, and using closed-loop systems. 2. How does building this soil sponge with compost or biochar help plants? Consider how these amendments affect water retention, nutrient availability, and soil structure. 3. How much water can hydroponics and vertical farming save compared to traditional soil farming? Remember the percentages we talked about in the case studies. These systems can use up to 90% less water. Take a minute to think, then we'll go through the answers as a class. Let's go over the answers to our review questions. 1. The 3 components of water smart farming are: build the soil sponge, match water to crop demand, and close the loop. 2. How compost and biochar help plants. They increase soil organic matter, which improves infiltration, holds water like a sponge, and reduces the need for irrigation. 3. Water savings with hydroponics and vertical farming. These systems can save up to 90% of water compared to traditional soil-based farming, making them very efficient, especially in water-scarce regions. Remember, these strategies are all about using water wisely, keeping it available for plants, and reducing waste. Let's wrap up Module 5 by highlighting the key takeaways. First, we need to work with nature. Building healthy soil helps it hold more water, which makes crops stronger during droughts and heat waves. Second, we should match demand smartly. That means growing crops that make sense for the local climate and using precise watering tools to cut down on waste. Third, it's important to close the loop. Whenever possible, recycle and reuse water so that every drop counts. And finally, we must think about climate and water together. Farming isn't just about today's weather, it's about preparing for changes in rainfall patterns and planning for future risks. This is a mind map of the whole module. It gives us a big picture view of how water and climate are connected to farming. On the left, we see every drop tells a story. This section explains where California's water comes from: aqueducts, rivers, snowmelt, and dams. In the middle are the climate knobs: global warming, earlier snowmelt, and more erratic precipitation. These are like dials that change how much water we have and when. Notice the impacts listed underneath: more irrigation needs, more intense droughts, and less predictability. On the right, we have water-smart urban farming. This is about solutions: building the soil sponge with compost and biochar, matching water to crop demand with tools like drip irrigation, and closing the loop with hydroponics, vertical farming, and water reuse. This mind map shows us that while climate change creates challenges, there are practical strategies to keep farming sustainable. This slide shows how learning about water in agriculture connects to real-world careers. There are three broad pathways. First, policy and governance. These are the people who shape water laws, plan for droughts, and manage resources at the city or state level. Careers here include water policy analysts, climate advisors, and urban water managers. Second, science and technology. These are researchers and engineers who study water systems and design solutions. Examples include hydrologists, meteorologists, climate modelers, and operations engineers. And third, agriculture and land stewardship. These are the boots on the ground experts helping farmers. Careers include soil scientists, irrigation engineers, farm advisors, and water treatment operators. Coming up, you'll get a chance to engage in 3 hands-on activities that cover the various concepts covered in this module. First, Water Lift Lab, from source to city, where you literally pump water from different sources into a city cup and track how distance and elevation drive energy cost, plus how conservation reduces both water use and energy tickets. Second, Run the Reservoir, where your team manages a reservoir through winter, spring, and summer, meeting urban and farm demand while avoiding floods and shortfalls as climate scenarios like early snowmelt and atmospheric rivers change the rules mid-game. And third, More Crop Per Drop, where you test a water-smart strategy like compost/biochar, mulch, drip, or hydroponics. Collect weekly data and argue which method gives the best crop per drop with the least water.